Okay, so hello everyone. So thank you very much for having me at the last minute. I know it's been quite hectic because my supervisor couldn't make it. So in this workshop, I'd like to talk about what Daryl and his team, including myself, have been working on for the last few years on sort of constructing a geometric framework for deriving stochastic equations that could be used in GFD modeling. So by the end of the talk, I hope to convey that geometry is a friend and it could be useful for deriving some stochastic equations. So in terms of the structure of the workshop, first I'd like to motivate why we need to introduce stochasticity in weather or climate models. And then I'd like to spend a good amount of time talking about the geometric structure of incompressible fluids. So what I mean by this is the Hamiltonian structure of fluids. So can I just to know my audience, who's quite familiar with Hamiltonian mechanics? Like, is anyone familiar with Hamiltonian mechanics, kind of? Okay, that's good. So I'm going to talk about the Hamiltonian structure of fluids, basically. And then using the Hamiltonian structure, I like to derive a stochastic model that preserves certain properties that the fluid models have. And then in the end, I'm going to talk about some conservation law that this new stochastic model has, and then show you some numerical simulations. So well, why do we need to add stochasticity in our weather or climate models? Well, basically, you know that it's possible to model the weather or climate at all the relevant scales of motion. I think this is right. Okay. It's very impossible to model the weather or climate at all the relevant scales of motion because it's just computationally too expensive. So what we do is we solve the equations of motion by solving it in a really coarse grid, and we try to account for the effects of the subgrid scale by a parameterization scheme. But there's a lot of uncertainty in what happens inside the unresolved scales. And also, if you look at the Lagrangian tracers of the spaghetti plot, you can kind of see that the Lagrangian trajectories essentially follow a sort of stochastic path. So it's natural to consider a stochastic scheme to model weather or climate. But the difficulty is that there's no one unique way of adding noise to your system. But fluid equations, just like any other mechanical systems, is a consequence of the Newton's laws, is F equals ma. So ideally, we would like to add the noise such that it preserves this structure. So one popular way of adding the noise is the stochastic perturbation by physical tendencies, which is basically adding the noise in the forcing. So you're adding the noise that models the uncertainty of your forcing term. So this is done in this scheme, which is used in state-of-the-art weather models in the Met Office. But what we would like to do is to add the noise at a more sort of fundamental level. So we want to add the noise that accounts for the uncertainty in the transport of our fluid velocity. So that means we're adding the noise in the A part here instead. So this idea is actually not new at all. So some people have been working on this. So Mikulevicius and Rozovsky has considered a similar idea where they added the noise in the transport term by using Newton's laws, by balancing the forcing with the uncertain transport of the fluids. And Etienne Memin has recently derived the stochastic fluid equation that preserves the energy. So what we would like to do is to derive a stochastic fluid equation from principles of Lagrangian or Hamiltonian mechanics so that it acquires all the benefits of Lagrangian and Hamiltonian mechanics. Like if you want to consider a stochastic model for more complicated equations, you can do this by this framework. So my supervisor, Daryl, often likes to talk about the Lagrangian framework, but I have a preference for talking about the Hamiltonian side. So I'm actually going to talk about the Hamiltonian point of view of these equations. All right, so let me talk about the geometric structure behind incompressible fluids, so like the Hamiltonian structure. So in the modern understanding of Hamiltonian mechanics, you can understand how to obtain the equations of motion by plugging in what is called the Hamiltonian function, which is the physical energy, inside an algebraic operation called a Poisson structure, and then that allows you to get a Hamilton's equations of motion. So the idea behind obtaining a stochastic equation of motion is that we add the noise at a more fundamental level, so at the level of the Hamiltonian, and then we plug this sort of stochastic Hamiltonian inside the Poisson structure to get a stochastic Hamilton's equation that models the fluid equations. So that's the general idea of what I'm going to be talking about. But in this part, I'm going to mainly talk about what the Poisson structure for fluids are and how it's derived. So just going back to the basics. So classical Hamiltonian mechanics, as opposed to the modern view of Hamiltonian mechanics that use Poisson structures, can be, so in Hamiltonian mechanics, you can obtain the motion completely by determining two factors. So one is the Hamiltonian function, which describes the energy of your system. And the second is the configuration manifold. So the configuration manifold is all of the possible states that your mechanical system can be in. For example, if you have like a pendulum, you know that your pendulum can only be in a circle, and therefore your configuration manifold is a circle. So on a manifold, you have a natural construction called a tangent bundle. So the tangent bundle is basically like a manifold, but at each point in the manifold, you have a vector space attached to it. So physically, you can think of this as a space of all the positions and the velocity. Like the position is the position on the manifold, and the velocity is like the vector that's attached to the tangent space at the point. So you can think of this physically as a space of position and velocity. And then there's like a dual notion of the tangent space called the cotangent bundle, which physically is a space of all the position and momentum. So in Hamiltonian mechanics, the cotangent bundle is a natural phase space. So the Hamiltonian is a function it's a function on the cotangent bundle. So this is a natural space to consider. So I'm not going to talk about the details of Hamiltonian mechanics here, but all you need to know is that once you have a configuration manifold and you have a Hamiltonian that's defined on the cotangent bundle, then you can derive equations of motion from this. So what is the configuration manifold for incompressible fluids? Well, you can understand fluids as a deformation of this fluid field on a manifold. So a natural candidate for the configuration manifold would be the set of volume-preserving diffeomorphisms on your manifold. So what I mean by that is it's a set of all the smooth invertible maps such that the Jacobian is equal to 1. So the Jacobian condition is necessary for the volume-preserving part. So if you impose this condition, then your diffeomorphism is volume-preserving. So the nice thing about this space is that if your underlying manifold M is compact, then the volume-preserving diffeomorphisms on this manifold is a manifold. So it's an infinite dimensional manifold. And moreover, it's a group by defining the group action as the composition of diffeomorphisms. So you have the identity diffeomorphism, which does nothing, and then two diffeomorphisms you compose together, it gives you a diffeomorphism. And for any diffeomorphism, you have an inverse diffeomorphism. So this is a group as well. Okay, so a very important concept in fluid dynamics is the Lagrangian and Eulerian description of fluids. So in short, in Lagrangian description of fluids, I mean, I think a lot of you are comfortable with this, but so in the Lagrangian description, your fluid is understood as the motion of Lagrangian particles, so like how the fluid particles move. But opposed to this, the Eulerian description, what it describes is how the velocity field at each spatial point evolves in time. So that's the difference between the Lagrangian and Eulerian. So this is going to be quite important in what I'm going to talk about soon. So if you're given a diffeomorphism phi, so I'm going to denote all my diffeomorphisms as phi from now on. Your trajectory of the fluid particle, I'm going to denote by the diffeomorphism phi acting on the fluid particle labeled capital X. And then I define this Lagrangian velocity to be its time derivative. So the Lagrangian velocity is the velocity at time t of your fluid particle labeled X. So now, okay, so if you assume that at time t, your fluid particle capital X occupies this spatial point little x, then you can write your capital X as phi inverse of little x. So then you can rewrite your velocity as a function of the spatial point little x, which is phi dot phi inverse of little x. So this velocity that we defined as a function of the spatial points, we say to be the Eulerian velocity. So we define the Eulerian velocity as phi dot phi inverse, which is the velocity at the spatial point little x. Right, so what is the Hamiltonian for incompressible fluids? So here I take my Hamiltonian to be just the total kinetic energy. So what I mean by that is if you take the Lagrangian velocity, I take the square of the Lagrangian velocity and integrate over the whole fluid labels. And rho is the mass density, which I take to be constant because I'm only considering a homogeneous fluids for now. So this is essentially like half mv squared, right? So now we have a Hamiltonian and we have a configuration manifold for fluids, so we can obtain, we can derive a Hamilton's equations of motion. But the problem with this is that your space is too abstract, it's too complicated. It's the cotangent bundle of the diffeomorphism group, which is an infinite dimensional manifold. So this is too difficult to consider for practical purposes. So we need to do a bit more work to get a useful equation for fluids. And the way to do this is using the symmetry of your Hamiltonian. So by using the symmetry of your Hamiltonian, you can squeeze out the symmetry to obtain a simpler equation downstairs. So you basically squeeze out the redundant symmetry inside the Hamiltonian to obtain a simpler equation. So that's the idea. And the two important concepts that allow us to do this is the symmetry of your system and something called a Poisson structure. Right, so the symmetry of your fluid. So what I mean by symmetry is it's any transformation that leaves your Hamiltonian invariant, okay? So if we consider this action of the diffeomorphism, so if we take any volume-preserving diffeomorphism psi, and we precompose the diffeomorphism by the diffeomorphism phi, then my Hamiltonian becomes this expression here. Then now I use the normal change of variables. So let's say that my psi of x is equal to y, and then I do a normal change of variables theorem to get this the Jacobian thing out here. But then we noted that your psi is a volume-preserving diffeomorphism. So in particular, the Jacobian is equal to 1. And therefore, you recover the same Hamiltonian. So this is saying that your Hamiltonian is invariant under the right composition of the volume-preserving diffeomorphism. So we call this symmetry a particle relabeling symmetry. And pictorially, what it says is, if you imagine like all the fluid particles labeled by colors, we're essentially kind of like recoloring this, and that wouldn't change the dynamics of your system. So that's the symmetry in your Hamiltonian. Right, so now let's choose our diffeomorphism psi to be the phi inverse itself and see what happens. So this is our Hamiltonian, and then we use the relabeling symmetry to write the phi and phi dot as phi, phi inverse, phi dot, phi inverse. I'm just precomposing this by the diffeomorphism phi inverse. So you notice that phi, phi inverse is just the identity map, and phi dot, phi inverse is the Eulerian velocity that I just introduced. So now we can write our Hamiltonian as a function of the diffeomorphism in its Lagrangian velocity to a function of just the Eulerian velocity field. So the particle relabeling symmetry allows us to go from the Lagrangian description of the fluids to the Eulerian description of the fluids. Right, so our Hamiltonian now in the Eulerian field looks like this. So this is just the velocity field squared and integrating over the whole space. And you can also write this in the vorticity form. So vorticity is the curl of U, and you can write it like this. So remember that we couldn't find a useful Hamilton's equations on the space T star diff vol because it was too complicated. But then I asked whether we can obtain a Hamiltonian system instead on the Eulerian fields U or omega. So we couldn't find a Hamilton's equations in the Lagrangian variables, but can I get Hamilton's equations on the Eulerian variables? So it turns out that you can, but we need to introduce an extra structure to do this. So this is the Poisson bracket. So I mentioned earlier that in the modern way of understanding Hamiltonian mechanics, you can derive a Hamilton's equation by plugging in a Hamiltonian inside a Poisson structure. So what I mean by a Poisson structure is if you're given a manifold P, a Poisson bracket is just a map, a bilinear map on the functions of P, such that it satisfies these three properties. So one is the anti-commutative property. So if you switch your F and G, you get a minus out here. The second is the Leibniz rule. So this is kind of like the product rule for Poisson brackets. And finally, it satisfies the Jacobian identity. So any bilinear bracket that satisfies these three conditions is called a Poisson bracket. And why this is useful is because it allows us to sort of define a generalized Hamiltonian system. So if you're given a manifold P that's equipped with a Poisson bracket, then a path in your manifold is said to satisfy the generalized Hamiltonian system with Hamiltonian H if the rate of change in time of your function evaluated at this path is equal to the Poisson bracket of the function with the Hamiltonian. Okay. So this is for any function as well. So this is the definition. So this is kind of like redefining my Hamiltonian system. So this is a more generalized Hamiltonian system. So before, I was only able to define Hamiltonian systems in cotangent bundles, but then now we can define a Hamiltonian system in any manifolds, provided that you have a Poisson bracket defined on it. So let's take an example. So if we take F to be the Hamiltonian itself, then by this definition, the rate of change of your Hamiltonian evaluated at this path is equal to the Poisson bracket of Hamiltonian with itself. And then by using the anti-commutative property of the Hamiltonian that we saw, of the Poisson bracket that we saw earlier, we can write this as minus the Poisson bracket of the Hamiltonian with itself. And this is only possible when this is equal to 0. So this kind of has so this proves the conservation of energy. And the conservation of energy is basically embedded in the definition of your Poisson bracket. Okay? So let's look at an example. So this is the standard Hamiltonian system on the cotangent bundle written in the coordinates. And I'm going to claim that this is also a Poisson system. It's a Hamiltonian system in the Poisson sense as well. So I claim that this is a Poisson system with the bracket given by this here, so dfdq dhdp minus dfdp dhdq. So in order to see this, let's take any function f, and we take its time derivative. And then by using the chain rule, we have dfdq dq dt plus dfdp dp dt. But then by using equation 1 here, the standard Hamilton's equations, you can write this as dfdq dhdp minus dfdp dhdq, which is the Poisson bracket here. So essentially, the generalized Hamilton's equations in this Poisson sense with this bracket is equivalent to the standard Hamilton's equations in this phase space. So why did I introduce this Poisson structure? It's because I claim that the incompressible fluid equation is a generalized Hamiltonian system. So it's a Hamiltonian system in a generalized sense in terms of the Eulerian variable. So it's not a Hamiltonian equation in the standard sense in terms of the cotangent bundle, but it's a Hamiltonian system in terms of Poisson brackets. So let's see how this works. So in order to do this, we use something called symmetry reduction. And what symmetry reduction is it's kind of the cornerstone in geometric mechanics. But what it allows you to do is to go from a complicated equation, Hamilton's equation on a complicated space, and provided that your Hamiltonian is invariant under some symmetry, you can squeeze the symmetry out to get a generalized Hamiltonian system on a more simpler space. And then we're happy. We can do some stuff with it. So in terms of fluids, we had the Hamilton's equations on this complicated manifold, which is the T star diff vol. And then we had this relabeling symmetry in the Hamiltonian. So we hope to sort of squeeze out the symmetry in the Hamiltonian to obtain a generalized Hamiltonian system in this simpler space, which turns out to be the space of vorticity. And then by using something called a Lie-Poisson reduction, you can essentially get a Hamiltonian system in the reduced space, but it's a generalized Hamiltonian system, not the standard one. So if you do this, the reduced space, which is the space of vorticity, acquires a Poisson bracket, which is called the Lie-Poisson bracket, which looks like this. So dfd omega and dHd omega are vector fields, and the bracket here is the standard commutator of vector fields. So now, by using this reduction technique, we have gone from a standard Hamiltonian equation on this complicated space to a generalized Hamiltonian system in this sort of simpler space. And you can also think of this as going from the Lagrangian description of your fluids to the Eulerian description of your fluids. Okay. So now let me show that this Hamilton's equations turn out to be equivalent to the vorticity equation that we all know. So this is the Poisson equation, the generalized Hamilton's equations, which is called the Lie-Poisson equation. So this looks like this. But then after doing a lot of calculations, you can show that this is basically equivalent to the vorticity equation that I write like this. So this LU, so this is the Lie derivative, which is sort of a generalization of the directional derivative, like u dot grad omega. So this is the vorticity equation. So your vorticity equation is equivalent to the generalized Hamilton's equations. Okay, right. So now that we have a Hamiltonian structure for fluids, I'd like to derive a stochastic equation based on this Hamiltonian structure. So, okay, so I feel like I have lost some of you at this point, so I'd like to kind of summarize what I've been talking about before. And so basically the most important thing is that your fluid motion is a Hamiltonian system in a generalized sense, with the Hamiltonian given by the kinetic energy, and it's equipped with the Poisson bracket, which is the Lie Poisson bracket here. So that's pretty much all you have to know at this moment. And as I showed you before, we want to derive a stochastic equation by plugging in a sort of stochastic Hamiltonian inside the Poisson bracket in order to get a stochastic Hamilton's equation. So that's what we want to do here. So this idea has actually been around, around since the 80s by Bismuth, where he considered something called the stochastic Hamiltonian system. And what that is, so the setup of this is, if you give in a Poisson manifold and a list of Hamiltonians, so like a tuple of Hamiltonians H0 to Hn, so this is not just one Hamiltonian, but in this case you have to consider a lot of Hamiltonians, so this is a multi-Hamiltonian system. And we consider a list of semi-martingales as well. So you have a list of, so a tuple of Hamiltonians and a tuple of semi-martingales. Then we can define something called a stochastic Hamiltonian system as any semi-martingale on the phase space such that it satisfies the stochastic Hamiltonian. So any semi-martingale on the phase space is said to satisfy a stochastic Hamiltonian system if you choose any function on your phase space. The function evaluated at this path satisfies the following stochastic differential equation. So it's df is equal to Poisson bracket of f with the h0. So h0 is the Hamiltonian for the drift part, plus the sum of the Poisson bracket of f with the noise Hamiltonians, and then Stratonovich dBi. And intuitively, you can kind of write this in this form, where you're basically plugging in a sort of stochastic Hamiltonian inside your Poisson bracket. So this is the Hamiltonian h0 dt plus hi Stratonovich dBi. So that's the intuition behind this. So instead of adding one Hamiltonian to get a deterministic dynamics, you're coupling a lot of your Hamiltonian with the semi-martingales and plugging into the Poisson structure to get a stochastic Hamiltonian equation. So for our fluid case, we take our Hamiltonian for the drift part to be the kinetic energy, as we showed before. And we choose our noise Hamiltonians to be of this form here, where psi I are arbitrary vector fields. So this is not a canonical choice. So we have to choose this by ourselves. And I'll talk about how we can choose this in the numerical simulation section later. But we choose these Hamiltonians. So we plug in the stochastic Hamiltonian h0 dt plus the noise Hamiltonians with the dBis, and plugging into the Poisson equation, we get the generalized stochastic Hamiltonian system. And then by doing some calculations, we can show that this is equivalent to the stochastic vorticity equation that looks like this. So essentially, we pick up this extra term, which is the Lie derivative of omega with respect to psi, and then coupled with this semi-martingale here. So we call this the SALT equations, which is a short for stochastic advection by Lie transport, because you can think of this, you can interpret this as the vorticity field omega being advected along a stochastic velocity field, which is u, and then the psi dB. So you have the omega being advected along a stochastic velocity. So this is a bit more easier to understand in terms of the Lagrangian viewpoint. So from a Lagrangian viewpoint, what this is saying is that your Lagrangian trajectory, which is given by x composed with this diffeomorphism phi, so it's saying that the Lagrangian trajectory satisfies a stochastic differential equation instead of deterministic one. So it satisfies this SDE. And this is essentially what we wanted, because we wanted to consider a model that models the Lagrangian trajectories as a stochastic path instead of a smooth one. Okay. So now let me talk about the conservation laws that's present in the system. So, so there's two very important conservation laws associated with generalized Hamiltonian systems. So one is the Casimir's, which is the conservation law that comes out of the sort of the degeneracy of the Poisson structure. So this is only related to the Poisson structure, not the Hamiltonian itself. So it's kind of like a kinematic conserved quantity. And the second one is the Noether quantity, which is sort of the conservation law that arises due to the symmetry of your Hamiltonian. So this is something called the Noether's theorem, which relates the symmetry of your Hamiltonian with a conservation law. And this is the conservation law that arises due to symmetries. Right. So Casimir's, again, as I said, is something that depends on the Poisson structure only. So if you're given a Poisson structure, we say that a function is a Casimir provided that your C commutes with every function in the phase space. So it's any function that commutes with any other function under the Poisson bracket. So this is called the Casimir. So it's kind of like the degeneracy of your Poisson bracket. So if you have a Casimir C, then because of the generalized Hamiltonian system, the rate of change of your Casimir is equal to the Poisson bracket of Casimir with the Hamiltonian. But because your C commutes with every other function, this is going to be equal to 0. So in particular, your Casimir is a conserved quantity. So for fluids, I'm going to gloss over the details, but in 2D fluids, your Casimirs are given by the following. So it's the integral of any function of your vorticity. And in particular, if you choose your function to be just a square function, then this gives us the conservation of entropy. So in 3D, you have a Casimir, which is the helicity, which is the dot product of the vorticity and the velocity. So this is kind of like the geometric interpretation of what the conservation of entropy and helicity means. Right. So now let's talk about the other important conservation law, which is which arises due to the symmetry of your system. So this is a consequence of something called the Noether's theorem, which relates symmetries in Hamiltonians to conservation laws. So if you have a differentiable symmetry in your Hamiltonian, then this gives rise to a conservation law. So that's the Noether's theorem. So for incompressible fluids, we saw that your symmetry is the particle relabeling symmetry. So your Hamiltonian is invariant under particle relabeling. So by Noether's theorem, this should give rise to some conservation laws. And it turns out that this is equivalent to the Kelvin circulation theorem, which states that so given a material loop, so like any loop that is advecting along a Lagrangian path, then you have this quantity, which is the circulation, which is the momentum per unit mass integrated along the material loop. So Kelvin circulation theorem states that the circulation is an invariant quantity. So it turns out that this quantity, the circulation, is the conserved quantity that's related to the particle relabeling symmetry in Noether's theorem. So what does the what does the Kelvin circulation theorem and the stochastic case look like? So now instead of having a loop that's being advected by a smooth velocity, you have that the material loop is being advected along this stochastic path. So the Lagrangian, sorry. Huh, where's it gone? Okay. Right, so now your stochastic path is being advected along a stochastic Lagrangian path, which is given by the stochastic differential equation here. So if you want to compute the evolution of the circulation, so here we use the Stokes theorem to go from the velocity interpretation to the vorticity interpretation of your circulation. And then we use something called the Kunita-Ito-Wenzel formula, which is like a generalization of chain rule for stochastic processes on tensor fields to get this. So inside the integrand, you have this expression here. But notice that if this is equal to 0, this is just the salt equation. So what it means is that if your vorticity satisfies the salt equation, then this satisfies the stochastic Kelvin circulation theorem, which states that your circulation is preserved along a stochastic Lagrangian path. So this is quite important because it's kind of like the Lagrangian description of the salt equation. So it says that your stochastic vorticity equation is has an equivalent interpretation as your circulation being conserved along a stochastic Lagrangian path. Right, so let's see what properties are conserved in our salt equation. So first we saw that our Casimirs are conserved because the Casimirs only depend on the Lie-Poisson structure, or so the Poisson structure. But we haven't changed the Poisson structure. We kept the Poisson structure, but we only changed the Hamiltonian. Like we only plugged in a stochastic Hamiltonian. So your Casimirs are still preserved under the stochastic deformation. So what about energy? So it turns out that our energy is actually not conserved. And that's because our Hamiltonians do not commute under the Poisson bracket. So here you have the Poisson bracket of the Hamiltonian with itself, and that's equal to 0. But here we have the Poisson bracket of Hamiltonian with the noise Hamiltonians, but they don't have to commute necessarily. So by this, our energy is not a conserved quantity for this under the stochastic system. But then we have that the Kelvin circulation theorem is still satisfied. So the circulation is a conserved quantity because we still have the relabelling symmetry. And by Noether's theorem, you still have the conservation of circulation. Right, so in the remaining minutes, I'd just like to show you some numerical simulations that Daryl and his team has been working on. So this is a team that consists of Daryl Holm, Colin Cotter, Dan Krisan, Igor Shevchenko, and Wei Pan. So I couldn't find his picture in Google, so I had to substitute with this. So they have been working on this really tirelessly on simulating the salt equations, as far as I remember, since I started my PhD 3 years ago, in hope that it can be used for numerical weather prediction one day. So what their project is basically kind of doing a role play of weather prediction. And the way they do this is, first they have a toy model for the truth. So they kind of have they simulate the truth as the deterministic Euler equation that's solved in a really fine mesh. So it's a high resolution simulation of an Euler equation. So they say that that's the truth. And then they simulate the salt equations, the stochastic equations, in a coarse grid and see whether the salt equation captures the truth somehow. So this is just a simulation that they have done. So in the top row, this is the simulation for the truth, which is the fine scale PDE that's solved. The PDE that's solved in a really fine scale, but coarse grained in order to compare with the stochastic equations that's solved in a coarse grid. So in the middle row, this is a realization of the salt equation, so the stochastic differential equation. That's solved in a coarse grid. And this is another realization of the salt equation. So we see that because of the stochasticity, these two realizations are different, of course. So the noise in the salt equation allows you to explore different situations that your weather could have gone. And of course, it's also different from the truth because of the noise. We see that, like, let's say that this simulation is closer to this truth compared to this equation. So by simulating a lot of possibilities of what the weather could have been, the idea is that it can capture, well, we hope that the salt captures the truth somehow. And that's what they're trying to do to evaluate the performance of the salt equations. So I mentioned earlier about this size, the function size that appear in the noise Hamiltonian. So there's no one canonical way of choosing the size. So we need to compute this somehow numerically. And the way they do this is they first assume that the size somehow model the uncertainty in the subgrid scale. So what they do is they simulate the Lagrangian trajectories for the Euler equation solved in a really fine mesh versus the Lagrangian trajectory for the Euler equation solved in a coarse grid. And then they compare the difference, they look at the difference between the fine trajectory and the coarse trajectory to get this vector dx. And then they get these samples of dx for a lot of the time intervals. And, and then that's how they obtain like a sort of spatial correlation matrix of the velocities. And the psi's here are taken to be the eigenfunction of this spatial correlation matrix. And in theory, you have infinitely many of these psi's, but in practice, of course, you have to have some truncation of this. So they choose the first n vectors psi that correspond to the n largest eigenvalues. And this kind of is interpreted as sort of like the dominant frequency in which the uncertainties sort of lie in. Okay, so finally, okay, so I actually don't really know much about this part because I'm not directly involved in this project, but they've managed to also like develop a successful data assimilation algorithm based on SALT as the signal. So as far as I understand, so they obtained the stochastic, they managed to develop a data assimilation algorithm based on stochastic filtering, which is it's kind of a method of updating the distribution of your stochastic model conditioned on the observation that you get from the truth. So ideally, if you get some observation from the truth, you can nudge your stochastic paths to the truth a bit closer. So the important plot here is these two plots here. So in the bottom right is a simulation of the SALT. So the blue trajectories are a lot of the ensemble runs of your stochastic equation and the coarse grid. And the red trajectory is the true equation, which is the deterministic PDE solved in a really fine mesh. And we see that the SALT equation captures the truth quite well until after some time when it escapes the ensemble. So it does quite well until some time. But then, so this is without observing the data. So this is without the data assimilation. So in the top right, we have the plot of the distribution, the evolution of the distribution with data assimilation and without data assimilation. So in gray is the evolution of the distribution without observing the data. And in the red is sort of like the posterior distribution of your stochastic model after you observe your data. And you see that the posterior distribution, when you observe the data, seems to capture the truth quite well. So your truth seems to be inside the posterior distribution after you observe the data. So they've managed to kind of like develop a successful sort of data assimilation algorithm using the SALT as a signal. And honestly, I don't know much about the details, so I can only kind of give the vague idea here, but it seems like it's working. Okay, so that's actually it. So now the conclusions. So, so my main idea was that, well, fluid motion is a generalized Hamiltonian system. It's not a standard Hamiltonian system. It's a generalized Hamiltonian system with the Poisson bracket, which is given by the Lie-Poisson bracket. So your equation can be made stochastic by making your Hamiltonian stochastic. So if you add a lot of noise Hamiltonians, then you can get a stochastic equation out by plugging into the Poisson structure. So for this model, the stochastic equation, so the SALT, conserves the Casimirs and the circulation because, well, first of all, you have the same Poisson structure, so it has the same Casimirs. And the circulation because you still have the symmetry inside, which is the particle relating symmetry. But it does not conserve energy because the noise Hamiltonians and the deterministic Hamiltonians don't commute with each other. And also, the team has managed to also successfully develop a data assimilation algorithm based on this model. Right, so I actually didn't talk much about the GFD models. I only talked about incompressible models, but you can also extend this idea to more complicated GFD models, like let's say, Boussinesq equation or shallow water equation. And the way to do this is instead of just having a kinetic energy, we couple our field with additional advected quantities. So for, let's say, Boussinesq, we couple with the temperature field. And for shallow water, we couple with the height field. And for shallow water, we couple with the And then your Hamiltonian becomes a sum of the kinetic energy and the potential energy. And also, so this is a bit complicated, but a major change is that your configuration space now becomes not just the volume-preserving diffeomorphism group, but it's a semi-direct product, the group of the volume-preserving diffeomorphisms with the vector space where your advected quantity lives in. But the idea is the same. So you can also get a stochastic equation for GFD by plugging in the Lie-Poisson structure, plugging in a stochastic Hamiltonian into the Lie-Poisson structure for this semi-direct product Lie group, which is also well known, so it's not that hard in the end. Okay, so that's all. So this is some reference, and yeah, thank you very much for your attention.
Well, thank you very much for a beautiful talk, and there are questions.
Yes, thank you. The model does not conserve energy. So in practice, by using this stochastic model, you introduce some diffusivity or some viscosity. How do you control it? And I mean, what is its meaning? Right. Does it have to be the real viscosity of the fluid, or it's something else?
Right. Okay. So I'm actually not involved in the numerical side of the thing, but as much as I know, in the numerical simulation, they add an additional forcing term and a damping term to control the energy somehow. So I don't really know the details, but that's what they do to get the simulation running, if that answers the question.
Thank you very much. Can you please comment a bit more on the noisy Hamiltonians in terms of interpretation and so on? I guess, yeah. Thank you.
You mean to compute index size?
Yes.
This part. Okay, so I'm actually also very new to this. So I talked with Wei, who is also working on this 2 days ago, actually, because I had to make this presentation in a rush. So I honestly don't know that much, but the way he explained to me was that so you have this grid. So let's say that this is the coarse grid. And you take a fluid particle located at each of these coarse grid points. And then they run two simulations. So one is based on the Euler equation solved in a really fine grid. And one is based on the Euler equation solved in a coarse grid. So let's say that this is the fine simulation, and this is the coarse simulation. And then they take the difference between these two paths. And they do this at every point. And then that's how they get this vector dx, which is the difference between the fine scale simulation and the coarse scale simulation at each grid points. And then they do this for a lot of times, so like ti, t1, t2, and so on. And they compute basically, let's say this is dx1. A matrix dx1, dx2, and so on. Okay, so here I actually don't really understand, but what they do is they compute the matrix M times MT, something like that, if I remember. But so this has to be like a time-space matrix. I don't remember exactly, but they compute this. And then their xi's are found to be the eigenvectors of this matrix. So it's kind of like a spatial correlation somehow. And that's how they compute this. But okay, so I don't really know the details, but if you want to know the details, it's written in the paper, the top one here. So that's where they talk about all the details of how to compute the xi's and how they do the data simulation, because I'm actually not really familiar with this paper.
Other questions? Well, if not, let's think of a solution.